No. Screen. I don't know what you call it.
The projector thing.
The thing that rolls down.
You guys want to go up and help us?
The screen that
Go up
comes
and help
down.
us.
No, go up. The screen that comes down. You also put that there.
There we go. I have to paper I keep all the chapter homework on so the final I have thoughts about. If I had more organization, I would probably be like
I don't know. No. Official. That's like college.
Some of these terms really started almost like 120 years ago. One of the architects of this area is Emil Fischer. Fischer actually worked a lot on carbohydrates, which has a lot of hydroxyl groups, and they all have very, very different stereochemical possibilities. And we'll talk about that later. But one of the things that he started with was glyceraldehyde, which is molecular formula of glyceraldehyde is CH2OH, CHOH, and CHO. Now, glyceraldehyde has two different forms. Where they are pure, one would rotate the line in the clockwise direction or positive. So one molecule that would be rotating light in the positive direction. The other one would be rotating the light in the negative direction. And what Fischer did is to figure out that there is a kind of carbon. This is this particular carbon that is chiral because it has 4 different groups attached to it. And so you can look at it in 2 different ways. One would be, let's draw the structure. In one case, we can have the OH group. This is the hydrogen. And because it's a tetrahedral carbon, you have CH2OH and CHO. I'm abbreviating this to CHO. So these are the 4 different groups, and you can have it look like this. And then this is actually what we call the absolute configuration of this molecule. And Fischer, in order to have this 3-dimensional structure written in 2 dimension on a piece of paper, what he did is to came up with a way of doing this so that he looked at it from the, let's say your eye is here. we are looking at it downward, which means that the way it looks like would be on the right-hand side, you have the OH. On the left-hand side, you have the hydrogen. And in the back, on top, it would be CHO. And on the bottom, you'll have CH2OH. And that he wrote it. Again, I hope you appreciate that. This is a three-dimensional structure. So when you are looking from the top, on your right-hand side, you'll get the OH. On the left-hand side, you'll get the hydrogen. And the other two are in the back. One on the top, one on the bottom. But both would be in the back. So that's why I have drawn this way, dash and link. And that he abbreviated to this form. And this is what we call a Fisher projection. So whenever you talk about a Fisher projection, we just write straight lines. But what it indicates is that the particle line, the groups in the back, and the horizontal lines, the groups are coming up towards them. So it's essentially, let's use this. So those are the four colors, and from your angle, this is how it's going to look like in the Fisher projection. The green is the OH group, the blue is the hydrogen, and in the back, you have the red, which is the CHO, and the bottom one, black one, is CH2OH. So you always have to look Fisher projection in this way, all right? And even though you're writing straight lines, this is one line, this is the horizontal line. Okay? That's how you should look at it. And so these formula, therefore, you cannot just switch it. And since we have shown it like this, which is so you have shown the structure like this, right? So you cannot rotate it like this, because now you have to look it from this side. Okay. So you cannot just rotate that. And what he called this absolute configuration is that this is, with a capital letter, it's D. It's D-glyceraldehyde. And obviously the mirror image structure, where the H and the OH on the changes side, so this would be L-glyceraldehyde. Okay, so that's the B and L nomenclature for glyceraldehyde. And arbitrarily, now one problem with this is that he didn't know which one is positive and which one is negative in terms of the rotation. But one of them would rotate towards the right side or positive, the other one is negative. And he arbitrarily chose the D to be plus and the L to be minus. It turns out that later on it was confirmed he was 50%, he had 50% chance of being right, and he was correct. When the extracrystallographic study was done, like 50 years later, they found out that the D is actually plus and the L is the minus. So the plus and the minus are therefore experimental property of how the plane polarized light is rotating. Whereas D and L indicates how you write it on three-dimensional. So that is actually called the absolute configuration. The R and S came later. Obviously, we can also name them. If you look at this one, we can figure out that this is the lowest priority. According to the R and S nomenclature, this is number 1, this is number 2, and this is number 3. So H is already in the back, so you can say this is 1, 2, 2 to 3. It's clockwise direction, so this is R. So the R glyceraldehyde is also D-glyceraldehyde. D and L is the old nomenclature, and since we still use them, because natural protein is made up of amino acids, and they're all natural proteins are essentially L amino acids. So the nomenclature is still being used, even though it was coined 120 or 30 years ago. But a more advanced one is the R and S nomenclature. So you need to know kind of both of them. So in Fisher projection, therefore, as we mentioned, that you write state lines, the other important thing to recognize is that if you have carbon groups, the more oxidized group goes on top. Okay. In this case, if you figure out the oxidation number, you will see that this is more oxidized than CH2OH. And that goes on the top, and the bottom group is less oxidized carbon. Okay. So now, this is the way the Fisher projections are drawn. And you will see many, many molecules, like a straight chain molecule of glucose is this is the formula of D-glucose. And so why call it D-glucose? First of all, that the D and L nomenclature comes from numbering the molecule, such as in this case, this is carbon 1, this is carbon 2, 3, 4, 5, and 6. And this one has multiple chiral centers. Okay. In other words, this one is a chiral center. The 2, 3, 4, and 5, they all are chiral centers. So in the Fisher projection, the D and L nomenclature indicates, first of all, okay, draw the molecule so that all horizontal lines indicate groups or atoms toward you. Okay. That's first thing to do. And the top and the bottom are away from you. Third point is that more oxidized group goes on top. And starting from carbon 1, the farthest carbon that is still asymmetric or chiral, that's the one determines D or L. If you have hydrogen on the left, that is D. If you have hydrogen on the right, then it's L. So the farthest carbon that is chiral indicates D or L based on hydrogen on the left or right. Okay, left is D and right is L. So in this case, D-glucose, the reason we call it D is that carbon 1 is CHO, carbon 2 is asymmetric, that's a chiral carbon, 3 is also chiral, 4 is chiral, and 5 is chiral, 6 is not, because it's CH, 2 hydrogens left. So 5 is chiral carbon, that is the farthest away, and the hydrogen is on the left, therefore this is D. And that's how, if you have multiple carbons, that's how the D and L are determined. On the other hand, in R and S nomenclature, we have to figure out 4 different carbons that are chiral. For all of them, R or S nomenclature. So the D and L nomenclature is again historical and it's still being continued. That's why it's important that you recognize that. But more commonly, for organic molecules, we use R and S nomenclature. All right, going forward. So this is an example of the reaction where you can get a new chiral center formed. In other words, you started with a compound that is achiral. There's no chiral center. In the first molecule, the propene that we have drawn, and then you treat it with the peroxy acid. Now you introduce the oxygen across the double bond. So now we have created one particular carbon. This carbon is now chiral. Now it turns out that if you start with an achiral compound and you use an achiral reagent, then the molecule that you are getting, even though it's chiral, what's going to happen is you are going to get a racemic product. And you remember the definition of racemic product. Racemic means you have equal amount of the both enantiomers, the mirror image structures are there. So why that happens, then you have to consider how this reaction really goes. If we consider in 3 dimensions how this reaction would go, let's say we have across the double bond, you have 2 hydrogens here, and the methyl group, and another hydrogen. Now the approach of the peroxy acid could be from the top or from the bottom. And depending on that, you actually end up getting, in one case, if it comes from the top, you generate the epoxide this way. And I'm drawing that in the 2 dimension, and therefore the methyl becomes OH, and the hydrogen becomes a dash. So this is one molecule that is generated, but it can also come from the bottom, and therefore, again, So now, if we use the priority ranking, we can see that oxygen gets number 1. Okay. Then this carbon is number 2, and the methyl group is number 3. Hydrogen is already in the back. Therefore, 1, 2, 2, 3, this is R. And here, this is 1. Again, this is number 2. And methyl is 3. Hydrogen is already in the back. So this is S. So we get a mixture of R and S, 2 enantiomers of the epoxide that is generated. Even though it's a chiral molecule, we get equal amount of that, and therefore there will be no optical activity because it's 50% of each. Unless you separate them, then each one will be optically active. Okay. We actually need to discuss a little more, few more reactions and so forth. We'll continue with this discussion, but please read this part. Skip the section that I indicated that the 7.9, the fidelity axis is not included. So skip that and then go to the reaction 7.10 and 7.11. And then those are the discussions that will take place next time. All right? Any questions?
Yeah.
Yes. Which one? Okay, so the priority rule of oxygen obviously is higher than carbon, right? So that's number 1. And you have a carbon. Which one are you talking about? Here? Okay, so this is oxygen 1, carbon is number 2. This carbon and this methyl has HHH, right? And this carbon has CHH. Okay? Right? So this is a hydrogen. Okay, we'll discuss that again